All right, let's just jump right in. We're going to talk about a concept in physics that is, without a doubt, one of the most important, but also one of the most misunderstood ideas out there. I mean, this thing governs literally everything, from the first moments of the universe to its very last. It's the reason time only flows in one direction, and get this, it might even be the fundamental reason that you and I are here at all. And to really get why this idea messes with people's heads, we just need to start with a super simple question. What does the Earth get from the sun? I'm sure you're thinking, well, that's easy. We get light, we get heat, warmth, energy. Everyone says energy. And that feels right. It feels totally obvious. But it actually creates a pretty big puzzle. You see, for the Earth's temperature to be more or less stable, so the oceans don't boil away, the amount of energy we get from the sun has to be pretty much exactly the same as the energy we radiate back out into space, right? If we just kept soaking up energy without getting rid of it, the planet would just get hotter and hotter and hotter. So from a pure accounting perspective, there's no net gain of energy. It's a balanced budget. So that's the big question, isn't it? If the energy in equals the energy out, what is it that we're actually getting from the sun that makes everything possible? The answer is something way, way more profound than just energy. And to figure it out, we've got to go back a couple of centuries to a puzzle about the most important piece of tech of the day, the good old steam engine. So picture this. We're in France right after Napoleon, and there's this brilliant young engineer, Sadi Carnot. He's looking across the channel and seeing that the British steam engines are running circles around the French ones. So he sets out to understand the absolute fundamental principles of how you turn heat into work. And this wasn't just some academic thought experiment. This was about national pride, industrial power, and military advantage. Back then, even the very best steam engines were only about 3% efficient. Just think about that. 97% of the energy from the burning coal was just wasted. Carnot wanted to figure out what the absolute best-case scenario was. So he dreamed up a perfect, idealized engine in his head, one with zero friction, zero heat leaking out, to find out what the laws of physics themselves had to say about the limits of efficiency. Okay, so let's walk through his thought experiment real quick. It's a cycle. First, you add heat to a gas, it expands, and it pushes a piston. Bam, you got work. Simple. But here's the tricky part. To get that piston back to the start so you can do it again, you can't just run the movie backwards. You have to cool the gas down and squeeze it, which means you have to get rid of some of that heat. And that's the absolute key. To make the engine cycle, some heat has to be thrown away. And this was his genius insight. To make any kind of heat engine that can run over and over again, you simply cannot turn 100% of the heat into useful work. It's physically impossible. You are forced to dump some of that energy as waste heat into something cold, like the surrounding air, just to reset the whole system. That energy isn't gone, it's just not useful anymore for pushing that piston. So fast forward a few decades. A German physicist named Rudolf Clausius takes Carnot's ideas about engines and thinks, whoa, this isn't just about engines. This is about everything. He realized this concept of waste heat, of energy spreading out and becoming less useful, was a fundamental rule of the universe, and he knew he needed a name for it. He called it entropy. The easiest way to think about it is this. Entropy is just a measure of how spread out energy is. So low entropy means energy that's concentrated, organized, and useful, like a red-hot piece of metal. High entropy is that same amount of energy, but now it's all spread out, disorganized, and much harder to use, like the faint warmth that radiates away from that cooling piece of metal. And this led Clausius to formulate two of the most powerful laws in all of science. The first law of thermodynamics says the total amount of energy in the universe never changes, it's constant. But, and this is the big one, the second law says that the total entropy, the total spread outness of that energy, is always increasing. So while the quantity of energy stays the same, its quality is always, always going down. But why? Right? Why is this a one-way street? I mean, most laws of physics don't care if you run them forwards or backwards. So why does entropy only ever go up? Well, the answer came from another physicist, Ludwig Boltzmann, who had this incredible realization that it's not a strict ironclad rule. It's all about probability. See, Boltzmann's huge insight was that it's not technically impossible for all the spread out heat in a room to suddenly gather itself together and flow into your cold cup of coffee, making it hot. It's just
So fantastically, mind-bogglingly, ridiculously improbable that you would have to wait trillions upon trillions of lifetimes of the universe to ever see it happen. So for all practical purposes, yeah, it's impossible.
Here's a great way to think about it. A Rubik's Cube. There is exactly one way for it to be solved. That's a very specific, ordered, low entropy state. But how many ways can it be messed up? Well, there are over 43 quintillion ways. Those are the high entropy states. So, if you just close your eyes and start making random turns, what are the odds you're going to end up in that one single solved state? Basically zero. You're overwhelmingly likely to end up in a jumbled mess. The universe is just playing the same game of odds. It's always moving from unlikely arrangements to more likely ones. Okay, so now that we have this incredibly powerful idea of entropy in our back pocket, we can finally go all the way back to the beginning and solve our puzzle. If the Earth's energy budget is balanced, what is this magical gift from the sun that allows all of life to exist? And the answer is just so elegant. It's not more energy, it's better energy. The sun provides the Earth with a constant fire hose of low entropy. We get hit with highly concentrated, high-quality, organized energy in the form of a few very energetic photons of light. And here's the trade we make. For every one of those high-quality, low-entropy photons we get from the sun, the Earth radiates about 20 low-quality, high-entropy photons back out into the cold of space. The total energy is balanced, but we've taken in one neat tidy packet and sent back 20 messy, spread-out ones. We take an order and we export chaos. And in doing so, the universe's total entropy goes way, way up. And that difference, that gap between the order we receive and the disorder we create, is where everything we call life happens. Plants use that concentrated sunlight to build complex sugar molecules. Animals eat those plants to power their own complex bodies. And at every single step of the food chain, we are taking in low entropy and spitting out high entropy. In fact, some physicists even argue that life itself might be one of the universe's best inventions for speeding up the production of entropy. We are chaos-making machines. Now let's just zoom all the way out, because this idea doesn't just explain life here on Earth, it explains the entire story of the cosmos. Entropy is what gives time a direction. It is the arrow of time, always pointing from the ordered past to the disordered future. The entire history of our universe is just the story of entropy increasing. For the story to even be possible, the universe had to start in a ridiculously special, highly ordered, very low entropy state at the Big Bang. And ever since then, it's just been unspooling, moving towards more probable, more disordered states, creating things like stars, galaxies, and us along the way. And it will keep going until it reaches a state of maximum entropy, the so-called heat death, where everything is cold, uniform, and nothing interesting can ever happen again. But hold on, you're probably thinking, wasn't the early universe just a smooth, uniform soup? That sounds pretty disordered to me. And this is the final mind-bending twist. You have to remember gravity. Gravity likes to pull things into clumps. Over billions of years, it wants to make stars and black holes. So a universe that is perfectly smooth and uniform, where gravity hasn't had a chance to do its clumping thing yet, is actually a profoundly unlikely, highly ordered, low-entropy state. It's like finding a billion pencils all perfectly balanced on their tips. The much more probable high-entropy state is for them all to have fallen over into messy piles. So where has all this entropy gone? Well, thanks to the incredible work of physicists like Jacob Bekenstein and Stephen Hawking, we know that the entropy champions of the universe are, by far, supermassive black holes. The amount of entropy contained in these things is so staggering, it makes the entropy of all the stars in the universe look like a rounding error. It's not even close. So it might sound like entropy is this relentless force of decay, just marching us towards a boring, uniform end. But that's not the whole story. Think about pouring cream into your coffee. The moment before you pour, when they're separate, that's a simple, low entropy state. After you've stirred it for 5 minutes and it's completely mixed, that's also a simple, high entropy state. Neither one is very interesting. The magic, the beauty, the complexity, all the interesting stuff happens in the middle. It's in those few seconds where you see the beautiful, intricate swirls and patterns as the cream mixes into the coffee. That's the transition from order to chaos. And that's where we live. That's where life exists, where galaxies form, where anything interesting happens at all. We are living inside that brief, beautiful, complex swirl. We and everything we care about exist purely because the universe is on this grand, one-way journey from a highly ordered past to a disordered future. We are a temporary, intricate pattern that has emerged along the way. So the question this leaves us with is a big one. Knowing that our existence is just a fleeting consequence of this cosmic process, how will we make use of the little bit of low entropy we've been given?